Welcome back to Mr. Vaughn's classroom, where he makes math so easy, even I can do it.
Before we get started on this video, I'd like to ask you to please hit the subscribe button, give this video a thumbs up, and engage with a comment below. In this video, we are going to begin Unit 3, which focuses on similarity. This is Lesson 1 about scale drawings. The learning goal for this lesson is going to be for us to make a scale drawing. We do have one learning target for this lesson. That one says that I can dilate a figure given a scale factor and a center. For glossary terms, we're going to start out with dilation. A dilation with center P and positive scale factor K takes a point A along the ray PA to another point whose distance is K times farther away from P than A is. Triangle A prime, B prime, C prime, the green triangle, is the result of applying a dilation with center P and scale factor 3 to triangle ABC, the blue triangle. So what results is we take the original blue triangle ABC, we make every distance larger by the factor, so in this case, every point is taken 3 times farther. Therefore, every line on the new green triangle is 3 times larger than the original. This is dilation. The other glossary term that we have is scale factor. The factor by which every length in an original figure is increased or decreased when you make a scaled copy. For example, if you draw a copy of a figure in which every length is magnified by 2, then you have a scaled copy with a factor of 2. So you can see here on the bottom left we have the original figure, and on the bottom right we have the scaled copy with a scale factor of 2. So every line in the shape on the right is 2 times larger than the corresponding line on the original figure. Now that we're done with the introduction, let's go ahead and get started on the practice problems.
I'm once again asking you to solve this equation, and don't tell me we can't afford to get to the answer.
Practice problem number 1 says that polygon Q on the right is a scaled copy of polygon P on the left. So the blue polygon on the left is the original, and the green polygon Q on the right is the image. Number 1, the value of x is 6. What is the value of y? So what we can do to figure this out is, in order to set the two shapes equal, we're going to take 4 over x, since those are the original side measurements, and we're going to set it equal to 3, because that's the corresponding part to 4, over y, because y is the corresponding part to x. Well, they just told us that x is 6. So 4 over 6 equals 3 over y. Now we're going to cross multiply. So when we cross multiply, we have 4 times y, which is 4y, equals 6 times 3, which is 18. Now I need to get y by itself. To do that, we're going to do the opposite of 4y. So the opposite of multiplying by 4 is dividing by 4, but we're going to do it to both sides so that it stays even. The 4 divided by 4 becomes 1, and so we have y equals 18 over 4. But this isn't simplified yet. Both 18 and 4 can be divided by 2. So 18 divided by 2 becomes 9, and 4 divided by 2 becomes 2. So this is the simplified. Y equals 9 halves, or 4.5. Whether you prefer decimals or fractions. Now we can look at part 2. What is the scale factor? What did we multiply by in order to get the new image? Okay? So if we do this, what I can do is I can take the new size and I'm going to divide it by the original size. And you can do this with either one. So the first example, the new size is 3, and the original size was 4. So our scale factor was 3/4. If we multiply 4 by 3/4, we get 3. You could also do this with the new size. We have a new size of 9 halves. We had an original size of 6. If I have a fraction inside a fraction, all right, or if I'm dividing a fraction, this is the same as multiplying by its inverse. So instead of dividing by 6, I'm multiplying by 1 over 6. 9 times 1 is 9. 2 times 6 is 12. This is not yet simplified because 9 and 12 can both be divided by 3. 9 divided by 3 is 3. 12 divided by 3 is 4. And notice it doesn't matter whether we use the top numbers that they gave us or if we use the right side numbers that we figured out. In both instances, we found out that the scale factor was 3/4. That's what we multiply by to get the image or the new size. So 4 times 3/4 gave us 3, and 6 times 3/4 gave us 9 halves, or 4.5. I hope this makes sense to you about how we can find the value of a missing side on a scale copy, and how we can go about figuring out what that scale was. If you still have any questions about this, please feel free to leave a comment below.
You kids have it easy. Back in my day, we didn't have calculators. We had to use our noggins.
Practice problem number 2 is a really good problem, I believe, to help you understand when you are correct in setting up your comparisons to find your scale. The main key is that we need to make sure that when we are setting up these comparisons like we see in A through F, that what we are setting up, the ratio that we're setting up on the left, equals the ratio on the right in a valid way. So when we look here, AB equals 6. Well, I'm going to call that the long part of oval E. So let's call this long E. CD equals 3 is this shorter line on oval E that goes up. So let's call CD short E. When it says that XY equals 4, that is the long horizontal line inside oval F. So let's call that long F. And ZW is the shorter vertical line inside F. So when we are comparing these, let's use these descriptions so that we have a better understanding whether these equalities that they're setting up are legitimate equalities. So if I look at A, on top on the left I have 6, and we said that was the long E. And on the bottom we have 3, which we said is the short part of E. And then on the right, on the top is 4, which we said was the long part of F. And on the bottom we have A, which we said is the short part of F. So what you're really comparing here is that you're saying the ratio of the long part of E to the short part of E is equal to the long part of F in relation to the short part of F. And that's a valid comparison. We're comparing the long part of each oval to the short part of each oval. So if they are at scale with each other, they should maintain this ratio. The long line in each oval should maintain a proportion to the small line within each oval. So A would be a true equation. We're comparing the parts within one oval to the same parts in the other oval. Now let's look at B. We have 6 on top, which is the long part of E, in a ratio with 4, which is the long part of F. And then on the right, at the top, we have 3, which is the short part of E. And then on the bottom, we have A, which is the short part of F. So we are comparing the relationship or the ratio of the long part of one oval to the long part of the other oval, and we're saying that that relationship should be the same as the short part of E compared to the short part of F. And again, this would be correct. As the long line grows or shrinks on one, it should do the same ratio of change on the other. As the short line on one oval grows or gets smaller, the short line on the other oval should grow or shrink by the same ratio. And the key here, I either want to make sure that, like in A, I have my long parts both on top and then my short parts both on the bottom. Or, like in B, I have my long parts both on the left and my short parts both on the right. I want them to either be corresponding when I look left to right, or I want them to be corresponding when I look up and down. So A and B are true equations. So on option C, in the top left, we have 3, which is the short part of oval E. And on the bottom left, we have 4, which is the long part of oval F. And then on the right side, we have the long part of oval E. And on the bottom right, we have the short part of F. So here we are saying that the short part of one oval in ratio to the long part of the other is equal to the long part of one oval to the short part of the other. These are flipped upside down. We're comparing short with long and short with long. So, we're comparing short with long over short. And these are not going to give us the same ratios. We're not making a valid comparison. We're not like we were in A, where we could do the long of one with the short of the same, because we were comparing it with the long of the other with the short of the same. We had both the longs on top. We had both of their corresponding shorts on the bottom. In B, we had the long of each compared to the short of each, and both from oval E were on top, and both from oval F were on bottom. So that's what made B a valid argument. But now when we look at C, we've got the short of one on top and the long of the other, of the same one on top, but then we have the long of the other on the bottom with the short of the other on the bottom, and they're switched. So C is not going to be a true equation. We're not comparing the same things. When we look at D, we have 6 over 3 So this is the same thing we had up in A, where we have the long line in oval E with the short line in oval E. So far, so good. But when we look at the right side, notice it's the inverse of what we had on A. So now we're actually saying the short part of F on the top with the long part of F on the bottom. Again, we're not comparing the same thing. If I want to compare the long part of E in ratio to the short part in E, then I need to make sure that I'm comparing that like I did in A, with the long part of the other on top and the short part of the other on the bottom. D flips those, so now the comparison we're making isn't a true comparison. The ratios are not going to be the same, and therefore D is not a true equation. Option E. We have 6 over 4 on the left, just like we did in B. So on the left, we're comparing the long part of E over the long part of F. And that was fine to do. We saw that on the left side of B. However, on the right side of E, again, they inverse it. So now we've got the short part of F on top and the short part of E on the bottom. Now it's the inverse of what we did on B, so it's no longer a true statement. We're not making a valid comparison. We're comparing the long part of E in relation to the long part of F with the short part of F in relation to the short part of E. That part on the right needs to be flipped upside down. We've got to be making sure that we're matching up the correct parts. So E is not valid. And then the last one on this problem, on the left, we have 3 over 4. So we see that on the left side of C, that is comparing the short part of E over the long part of F. And on the right, we have the inverse of C, where we're now comparing the short part of F with the long part of E. Now, the problem with this is that we're comparing different parts. Because if you notice, on A, it was fine to compare long and short with long and short. But we needed to be comparing the long and short of the same oval, because they are going to change in relation to each other. If we start out with E, if we make AB grow, then CD is going to grow with it. They are changing at the same time, at the same rate. What we can't do is try to act like there's a comparison between the long part of E and the short part of F. They are not changing in relation to each other. So F would not be a true statement. When we're making these comparisons, we're allowed to do it in the two ways that they did in A and B. In A, I am comparing two parts of same shape. And then in B, I am comparing two shapes of same part. So in A, I was comparing the two parts of oval E with the two parts of oval F, and I made sure the same parts were on top and bottom. And then in B, I was comparing two shapes, but of the same part. So I was comparing the long parts of E and F with the short parts of E and F. And I made sure that the two parts for E were on top and the two parts on F were on the bottom. So I hope this makes sense to you. This is usually probably the trickiest part of understanding scale, how to set it up to find your scale when you know the size of the parts. So practice this. Make sure that you fully understand when you're setting up correct comparisons so that when you do your cross multiplication and then solve for your missing amount, that you're actually getting the correct answer for that. If you do still have any questions, please leave a comment below.
Tonight, we're looking for answers. Answers to the age-old question, why does the train from Boston leave 2 hours earlier than the one from New York? Because one of them is lying.
Practice problem number 3 is now going to help us practice the next step. In practice problem 2, we were making sure we understood how to set up these ratios so that they were equal to each other and they were valid. Now, once we have these equalities set up with valid ratios, now we need to know how to solve them so that when we have 3 of the parts, we can find the length of the 4th part. So for number 1, we've got 2 over 5 equal to x over 15. What we're going to do is we're going to cross multiply. So I'm going to multiply the number on the top left with the number on the bottom right, and that's going to give me 30. And then I'm going to take the number on the top right and multiply it with the number on the bottom left, and that's going to give me 5x. So now once I have 30 equals 5x, I'm going to do the opposite of 5 times x, which is divide by 5. But if I do it to one side, I've got to do it to the other side as well. Anything divided by itself just becomes 1, and so now I have my answer. 30 divided by 5 is 6, and that equals x. If you want to double check yourself, substitute your answer in for x. To go from 2 to 6, I would multiply by 3. To go from 5 to 15, I would also multiply by 3. Therefore, this 2 over 5 turns into 6 over 15 by multiplying by 3, so my growth factor would be 3. Now let's look at number 2. we have 4 over 3 equals x over 7. So again, I'm going to cross multiply. Top left times bottom right, 4 times 7 is 28. Then I'm going to take top right times bottom left, and that's going to be 3 times x, which is 3x. Now I need to get x by itself, so the opposite of 3 multiplied by x is to divide by 3. If I do it to the right side, I need to do it to the left side. Anything divided by itself becomes 1. So I now have 28 over 3 equals x. If I wanted to write this as a mixed number, that would be 9 1/3 equals x. So this is how we could find the missing x. Number 3. We have 7 over 5 equals 28 over x. I'm going to cross multiply top left times bottom right. 7 times x is 7x. Then I'm going to cross multiply top right times bottom left. 5 times 28 is 140. To solve for x, I'm going to divide by 7 on both sides. 7 divided by 7 is 1. So this gives me x equals 140 divided by 7 is 20. So my missing x is 20. If you wanted to double check that, put 20 in for x on number 3, and you can see that if you multiplied 7 by 4, you would get 28, and if you multiplied 5 by 4, you would get that missing 20. So the right side is 4 times bigger than the left side. And the last one, number 4, we have 11 over 4 on the left equals 5 over x on the right. We're going to cross multiply. 11 times x is 11x. 5 times 4 is 20. To get x by itself, I'm going to divide by 11 on both sides to keep it equal. 11 divided by 11 is 1. So we get x equals 20 over 11. Or, if I wanted to write it as a mixed number, x equals 1 and 9 over 11. So once you get your ratios set up properly and set equal to each other, this is how you solve for the missing variable. I hope this makes sense to you. If you have any more questions, though, please feel free to leave a comment below. Looking back on the learning target, we did have one And that simply says that you can dilate a figure given a scale factor and a center. And all that means is that if they give you a shape and they tell you what the scale of it is and where your center is, you understand that you are simply making the distance between each point and the center that many times bigger. So if your scale is 2, then you are making every part of that figure twice as big. So you're moving each point twice its first distance from that center point. We looked at how to set up the ratios into true equations, and we looked at how to solve for the missing variable when we knew 3 of the lengths, and we looked at how you could check that to make sure that you were multiplying by the same scale on the top and bottom to move from the left ratio to the right ratio. So I hope you have a better idea of what we mean by scale drawings and how we go about that. We're either multiplying by a number bigger than 1 to make the scale bigger, to go from a smaller shape to a bigger shape that has the same ratio dimensions, or we're multiplying by a number less than 1 in order to shrink it and go from a bigger figure to a smaller figure, but maintaining those same ratios of the portions. If you do still have any more questions, please feel free to leave a comment below. If you found this video helpful, in the bottom left, you'll see another video that YouTube is recommending for you. In the bottom right, you'll see a subscription button for the channel. It would really help out if you would subscribe. And give this video a thumbs up if you liked it. I look forward to seeing you in the next video.